Hello guys, today we are going to start the new topic about the system identification. Okay, system identification. It's important topic in the system dynamics and the control theory because we don't know everything about the R models or the physical systems, just like the DC motor or robot system or something like that. Okay, and so today we are going to build the theory and the application, especially in terms of what the least square estimation. Okay, these are topics, and so the objective of this note, this can be called the application notes because we are going to build the MATLAB code in order to design and test the R algorithm in the real-time systems. Okay, and so firstly we need to build mathematical model in terms of the mechanical and the electrical parameters of the watt of the DC motor, but from where? From measured data. In real life, you should collect the whole data coming from the DC motor, for example, the speed or the position values, and so these values can be used to identify your system parameters. Okay. After that, we need to create the discrete model. Because in real life we should always utilize the discretization for the collected data, because always we want to utilize the computers or the microcontrollers, which is based on the sampling rate. Okay, and so to define system parameters based on the sampling rate. Okay, after that we approach the model in terms of the first order modeling. Okay, in the DC motor we will use it. These three topics are the basis of the identification process for DC motor physical parameters or the electrical parameters, for example the inertia or the damping ratio or the PWM rate coefficients or the electrical constant. Okay, and so everything is accomplished with the least square optimization or error based identification. Okay, so in the first place we need to build the one and system modeling. Okay, suppose that at this case we should consider a rotational mechanical system via DC motor, can be represented with the J is the inertia factor, dWt is the angular speed divided by dt is the first differentiation, plus C times Wt, this is the loss energy factor in here, and so always we have the kV times ut parameter in here, just like this one, and so the parameters should be defined with the ut. In real systems we should always utilize the PWM rate in here up to the 0 to 100. Okay, and so if we select this parameter, and then we will find the kV, C and J based on this rate. Okay, Normally we should assign the voltage value, but in the real-time systems, especially driven from the MATLAB or the STM32 processors, and so we should assign it because we can only control the PWM rate of these terms, not the voltage one. Okay. And so if we build the R model based on these things, and so this KV, C, and J are appropriate with the real model. If you are using the voltage value, and so you have the wrong results in here. Just remember that, okay? And so this is the inertia, J, inertia, and C is the damping, damper coefficients, okay? So, in order to build our dynamics, we need to write the WT dot is equals to the minus C divided by J, WT plus KV divided by J times UT. Okay? And so, in a simple way, we build the R model based on these things, A times WT plus B times UT. You can easily find this coefficient is equals to the A, this coefficient is equals to the B. Okay, these are main information about the modeling techniques. Okay, so these are the general equation for to find out the parameters of the A and B. Okay, so in the second topic, we need to talk about the discretization. Okay? Because in real systems, we always collect the data based on the sampling rate. Okay? This is important parameters because if we have a high resolution, and so the R model is the best, but in many cases, we cannot reach the 1 millisecond or the 10 millisecond sampling rate to build or run or control your systems. Okay, and so in order to analyze these terms, firstly define the parameters like the Fs is the sampling rate, or 1 divided by Ts. This is sampling rate. Okay. This is equals to the It's equals to the STM32 sampling rate for for completing the whole codes in your computer. For example, if you have any main function, and also we have the while conditions. Okay, and so these while conditions, total process, total time is assigned with the Ts, not the main frequency sampling rate of the STM32. For example, the STM has the 216 megahertz, but this is not the R sampling rate. The sampling rate is equals to the one completion time for a given while loop in here. Okay, this is important. And so the K 0, 1, 2, blah blah blah, this is the index of the sampling process, and so the Tk, the main constant, K times Ts, it's the time. Okay, that the STM or the MATLAB builds your information. Okay, and so in order to discretize our system, we can use the forward difference equation, but in the basis of the Euler equation. Forward Euler equation. Like we can consider that the W dot is equals to the with the index of the WK plus 1 minus WK divided by TS. Okay, and then we should put this equation into the into the main equation, and then we will have in the discretization form WK plus 1 minus WK divided by TS is equals to is equals to A times WK plus B times UK. Okay, and so in a simple way we have the WK plus 1, and so we have also 1 plus ATS times wk plus b times ts u k. Okay, these are the general equation for the what, for the discrete process, and so the each step can be performed at separately from the previous or the forward one. Okay, if we know the wk, and so we can calculate the k plus 1, and so after that we can assign the next wk with these values, and so it's going on, and then we will have the whole the dynamics, but in the what, in the STM process or the MATLAB function or in the real-time operation. Okay, we cannot use the continuous function based on these informations. Okay, and so in a simple way our total equation is equalized with the what, the w k plus 1 is equals to the what, 1 minus c ts divided by j times w k plus kv times ts divided by j times u k. Just I'm putting the what, the a and b into the what, into the c divided by j, kv divided by j. Okay, I remove the a and b and I use the what, the main system parameters in here. Okay, and so this is also indicates what, the this can be considered a bigger a, this can be considered as a bigger b, and so the last equation is equals to what, the bigger w k plus 1 bigger w k plus 1 is equals to the a times w k plus b times bigger u k. This is the what, the our discrete formulation for a given the motor parameters. Okay, so how can we accomplish the what, the parameter estimation in here? Parameter estimation. So firstly we need to assume that the wk is what, is our measured data. For example, you test your algorithm on the real time, and so the t and the w can be collected with the what, with this nomination, and so this values is assigned to the what at each index for a sampling rate assigned to what, the measured data. And also we provide what, the uk in here, just like this one. This is the known input signal, which means that in order to create these values, for example, the u is assigned to what, for example, the 100 PWM rate, and so we should assign these values. And then in order to build our model, the bigger wk is assigned with what, the smaller wk. Okay, and so this bigger uk is assigned to smaller uk, right? Because the smaller uk is the known input signals. And then we can write also wk plus 1, this is the estimated values of these terms, and so wk plus 1 is also assigned to these values. Okay, and so our total equation can be built, the bigger wk plus 1 is equals to a times bigger wk plus b times uk can be assigned or built in another form, just like this one, wk plus 1, it's a bigger, and so we can collect the matrix form in here, wk and uk. This is a 1 times 2 vector, and also we should write to what, the a and b. Okay, so the multiplication of this matrix is giving with the what, wk plus 1, because the same idea, wk times A, UK B. But this is a special form for the what? For our least square approximation values, okay? And so this value is equals with the y, and this value is equals with the phi times this value is the theta, okay? And also just remember that if we are utilizing the k times 2 matrix, it's the dimension of the 2 times k matrix. For each index, we can calculate the whole formulation based on these informations, okay? So what is least square approximation? We can find this theta value a and b from this data because we have the whole time history in here, and so we have the k plus 1 value, wk value, uk value, and so we can easily find the a and b. The least square approximation is defined with this formulation. LSE gives us to what? The theta hat. It's the estimated value, which is equals to what? The phi transpose t, phi over minus 1. This is the inverse operator, and phi transpose 1, y, okay? And so the where this theta hat is equals to the what? The a hat, b hat, okay? This is our estimated parameters. If you calculate these theta hat values from the matrices or the measured data, and so we can easily find out to the what is the values of the a and b in estimated form. But we need to remember that our measured data is in the form of the discrete formation, and so the continuous time parameter should be recovered. Otherwise, we have the error, okay? Using the relation a hat, it's the estimated value, a hat minus 1 divided by ts. This is coming from the what? This is coming from the this formation. This is the greater a, and this is the greater b, okay? And so we can also write to the what? The b hat is equals to what? B, bigger b, divided by ts, okay? And so these are parameters. And then the c hat is the estimated damping value is equals to what? The minus a hat times j, coming from what? The system parameters, right? And so this is also equals to what? The minus a hat minus 1 divided by ts times j, okay? And also kv, electrical parameters, is equals to what? The b hat times j, which is equals to the what? This is kv times ts divided by j. It's coming from these terms, and times 1 divided by ts, okay? So this is our equation, and then how we can write the algorithm. 1 divided by 5. The algorithm is given by, for example, in the first place, the obtain the what? Wk value and Wk plus value and Uk value, which is coming from the what? The measured data, right? We possess it. Measured data. And after that, we need to calculate to the what? Calculate theta hat is equals to what? The phi t times phi over minus 1 phi transpose times y. And then the build to the what, we estimated k plus 1 is equals to the a hat is the estimated parameter, w estimated k plus b hat times uk. Okay, so after that, compare the results. Compare the results for both real and estimated value. Okay, if our model is correct, and so we will have to what, to our estimated model to be built in the what, in MATLAB or the real time or the physical parameters of these terms. Okay,